Hi. Sorry about the video just now for electric field because I forgot to connect the microphone, so there is no sound. You'll be watching video and without sound. So I will roughly go through this one again, but much faster speed. Now we come to the 1.3 electric field line here. We have positive charge, negative charge. The electric field line will have this pattern. They are exactly the same, except our positive charge, the electric field line is pointing away. This one pointing in. Okay, that is the only difference. The rest are the same. Okay, and then of course we are looking at the three-dimensional. Two-dimensional. If it is three-dimensional, you can imagine that you have a charge at the center and all direction. 360 degree in every direction, three-dimensional. But you only do two-dimensional, so don't worry about that. And then when we put two different charges together, they will going to attract each other. So when they attract each other, the electric field will be connected. Okay, so the shape is like this, and then the electric field will be starting from positive charge, end up in negative charge. Okay, so start from here, end up here. So this way direction is from the positive to the negative. And then when we have two positive charges put nearby, they will repel each other. So when they repel each other, what happens is they're going to have this electric field line not connected, trying to very close, but they don't touch each other. The line here, the dotted line here, is what we call the asymptote. Normally you learn that one in mathematics. And then since they are positive, so the electric field will be pointing out. If I change both these charges to negative charge, they will have electric field pointing in. Okay, now next one is 1.4 electric field calculation. Okay, but before calculation we need to look at the way we draw electric field vector. The first one is, let's assume you have a positive charge, okay, and then a point at the r away. That vector, the red one, is the electric field vectors, and then you see it must be a straight line, okay, from the center of the charge to that point, and then away or in. If this is positive charge, your vector will be here. If it is negative charge, then your vector will be pointing into the charge, starting from here to that charge. Okay, so look at that one in a moment. Now our electric field E is defined to be the force per unit charge at a point. So the formula is F/Q, and the unit will be Newton per Coulomb, or there will be another one, Volt per meter. Okay, and then the next one is this. Okay, other than this formula, we have a second formula, which is this one. Now, how do we get that one? Let's assume if you want to detect magnetic field, you need a compass, okay, like this. So this compass here have a very small magnet inside, and this magnet will be influenced by the Earth's magnetic field. So you see, you will use something, a small magnet, to detect a bigger magnetic field. Okay, same thing for electric charge. So if you want to know electric field around this charge, you need to use a very small test charge. Okay, so this is a test charge. We normally use a symbol Q0. So now you put a test charge here, you will know whether it get repelled or get attracted. If this one is positive, then it get repelled. If it is negative, it get attracted. Then you can tell whether it is a positive charge or a negative charge. Okay, so we go back to this equation number 1 here. Electric field is equal to the force divided by the charge. So we have F/Q0. But we also know that force is given by K, Q1, Q2 divided by the square of the distance. So when we put the force in, we get K, Q, Q0 over R2, because I assume Q1 is Q, Q2 is Q0. So we can end up cancelling the Q0 and giving us a formula E equal to KQ over R squared. Alright, so that is our second formula. Okay, now come to the next one. Okay, come to the next one. Drawing electric field vectors. Okay, drawing electric field vectors. We have, let's assume you have two charges, Q1 positive, Q2 negative. So at point A, you're going to have two electric field vectors. One is E1, which is away from Q1 because positive, so see, in a straight line, this dotted line. And then for the Q2 is negative, so you still draw the guideline, the dotted line, but because it's negative, the electric field point into the negative charge. Okay, so I use two colors here, the red one for the electric field from a positive charge and a blue one for the electric field from a negative charge. Okay, and then in this example, you have three charges, Q1 positive, Q2 positive, Q3 is negative. So that means you're going to have three vectors. The first thing you'll do is to draw all this dotted line, which is a guideline. Now we look at the Q1. Q1 is a positive charge, so the electric field must point away from the charge. So you see, it forms a straight line away from the Q1 because positive. So I label this one as E1. And then for the Q2, same thing. I have this straight line. This is a vector E2. And then for the Q3 is negative, so the electric field point into the charge. I use blue color, so you see a straight line there, so it's E3. Okay. Now come to calculation of electric field. Example 1. Start with a very easy example. You have Q1 equal to 2 microcoulomb, and then there are 2 points here. A, 40 cm away, and B, vertically below Q1 is 10 cm. Your A is horizontally away from the Q1. So now, first thing you'll do is to label, okay, the electric field. E1, okay, EA. Why don't I use a E1 and E2? Because this one you only have one charge, but two different locations. So we can use a subscript A to describe the electric field at point A, and then subscript B to symbolize the electric field at point B. It's much more convenient that way. So now, this one is positive charge, so it point away. This one also positive charge refer to B, so it's actually pointing away also. So that one is the labeling part. So we're going to calculate the electric field at A and B. After that, we follow the second part, the second step, which is find the magnitude. So our magnitude of EA is given by KQ1 over RA square. Make a good habit using a subscript, correct subscript, so that you don't put in the wrong distance. Okay. Now our K is already given here, and then our Q1 is 2 microcoulomb. The distance here is 40 cm, so we change to meter 0.4, and from calculator it gives us this value. And then EB, the same thing, is KQ1 over RB2 square. So 2 microcoulomb, again the same charge, but distance is shorter, 10 cm, 0.1, so this one is larger. And after that, after you calculate the magnitude, you get the vectors. Okay, vectors. EA pointing to your right hand side, that one is positive I. So at EA equal to positive 1.12, 10 to the power 5 I. Okay, and EB pointing down, negative Y, so we have negative J. Okay, so that is example 1. This is a very straightforward and very easy example. Alright, now come to the next one. Example 2. Our example 2 now, we have two charges, Q1, Q2 at the distance away. Okay, their distance is 0.7 meter. And then somewhere in the middle, B. So question is, find the net electric field at B. Alright, so both charges are positive, and midpoint B means it is 0.35 meter, 0.35 meter from both charges. Okay, so the distance are the same now. So first we label E1 is the electric field from Q1 because positive, so point away at point B. Q2 also positive, 4, so point away. Now my vector here is longer than this one, is simply because this charge is larger than Q1. Okay, then distance are the same, so definitely the electric field from Q2 will be much stronger. So larger electric field, the vector is longer. Alright, even though it points in the opposite direction. So that is labeling number step 1. Step 2, we calculate magnitude, same like previous example. Formula KQ1 over R square, so put in the value, we get this. And then for E2, same thing here, Okay, 4, and then this one we get 2.94 10 to the power 5 Newton per Coulomb. And after that, we vectorize them. Okay, we vectorize them. This is E1, vectorize, E1 pointing to the positive X, so positive I. And then E2 pointing to the negative X direction, negative I. Magnitude are the same. Okay, and then step 4, net force. We sum them up. Your E net is equal to E1 plus E2 and negative, this is our answer, negative 1.47 power 5 I. So that means, because this vector is stronger than this one, so it end up pointing to the left hand side. So that's why negative I direction. Okay. Now example 3, this is a difficult one. So now our example 3 here is 3 charges, Q1 positive 4, Q2 positive 7, Q3 negative 5. So calculate the net electric field at C, at this point C here. So this distance is 30 cm, 40. So definitely using Pythagoras theorem, you get this one 50. But you don't have to show the calculation here because this is a simple 3, 4, 5. Okay, and then first we label. So for Q1 is positive 4. So away, pointing away, I label this one as E1. And then this one is Q2 positive 7, pointing away also, but in this straight line. You see, for E1, straight line like this, E2, straight line, and then E3 is negative 5. So negative electric field point to the charge. So in this case is downward. So this blue color is for negative charge, E3. Okay. And then after that, use the same method to calculate the magnitude of the electric field. E1, this one, E2, this, and E3 is this one. Don't use a wrong distance. That's why we have subscript R1 for E1, R2 for E2, R3 for E3. By using that method, you won't make the mistake. And then step number 3, we change to vector. Now this question is slightly different is because we have E2. This is the criminal here. It's going to give you a lot of headache. So E1 is positive I. So we got no problem here, positive I. E3, this one is negative J. So negative J. Then when it comes to E2, it is making an angle theta with a horizontal line. This angle theta is the same as this angle theta here. So we can calculate the theta here. Tangent theta equal to 30 over 40, so we get theta 36.9 degree. Okay, now we're going to draw the vector E2 again, and we split it into two components, EX and EY. So our component EX is this value. Okay, after we put in the theta 36.9, the E2 is this value 2.54, 2.52 10 to the power 5. You multiply, you get this positive I. Same thing for EY, which is E2 sine theta. So you get positive J. After that, you combine them. So you get this. This is your E2. E1, E2, E3. So your next step is to sum them up. Okay, to sum them up. So your E net electric field is E1 plus E2 plus E3. So you write down the their final vectors here, and sum up. Finally, you get this. Okay, 4.27 power 5 I minus 3.48 10 to the power 5 J Newton per Coulomb. Alright, and then example 4, this one we're using a different formula. Let's assume you have electric field pointing to your right hand side, 120 kilonewton per Coulomb in positive I direction. Okay, so you have two particles here. One is a proton, another one is an electron. So find the force experienced by the proton and the electron. So you are given the charge of proton is this, the charge of electron is this. They have the same magnitude, but one is positive, one is negative. Initially, we don't know the direction of the force. Okay, we don't know the direction of the force. So here we calculate the force from this formula. Okay, here E equal to F over Q. So your F is equal to QE here. All right. So our first force is a force on the proton. Fp equal to QPE. Charge of proton is this one. Multiplied by the electric field. Don't forget the kilonewton. So in kilo you have another 30 and it's positive I. So finally we get the answer of positive I. This much here. So the force on the proton is positive I direction here. Positive I point in the same direction as your electric field. And then when you do the same calculation for Fe, the force on electron, our value are the same. Except that in this case, you're going to have a negative in front. So finally, your answer end up the same magnitude, but opposite direction. Negative I. So negative I means that your electric field, electric force for the electron is pointing to the negative X direction. Is opposite the direction of the electric field. Alright. So that's it. This is the update for the previous video which does not have sound. So sorry about that. So I had to watch 2 videos. This is a short one. The previous one is more detailed. So maybe someone can help me to create the sound otherwise. Okay. So keep updating for yourself.